Yeah, let's get started. All right, well, welcome to the Simons Institute and welcome to the first workshop of the semester, the Synthesis of Models and Systems workshop that's part of the program on Theoretical Foundations of Computer Systems. I'm very happy to have you all here. A big thank you to the organizers, Radu Grosu, Raz Bodik, Ruzika Piskac, and Sanjit Sashia. Enjoy the workshop. It's on almost every Monday through the semester. So I'll hand over to Ruzika.
Oh, thank you very much, and thank you all for being here. As Peter just said, it will be almost every Monday except next Monday, because next Monday is the President's Day, and also it won't be once the date which I now forgot when is actually the Richard Karp lecture, but. Anyway, that's almost every Monday. You can block now for the rest of the semesters. We hope to see you here and that we can see many interesting talks and many discussions about software synthesis. So the organizers are Raz, Radu, and Sanjit, and myself. And we kind of envisioned that this synthesis seminar will go through the following. Initially, we will have a couple of tutorials, and we are very excited today to have Bernd Finkbeiner to start this with the tutorial on reactive synthesis, because as you know, reactive synthesis is something that started this interest in the synthesis. And then after tutorials, we will actually have a theme of the day. So for every day, we will have a couple of talks. Program is still being created as we go. So it's a online synthesis of the program. And in each theme of the day, we will have a couple of talks followed by the students' talk. So we also ask you, if you have a student interested in synthesis, please motivate them to attend this. Like you can register for free. They can just be attend this. And, like we hope to have a very exciting work on the synthesis that won't only present what has happened in the synthesis, but that will also outline exciting new ideas that we hope will bring the research in the program synthesis a couple of steps further after these workshops. So that's about the workshop, and we kind of thank you all on the behalf of organizers for being there, and also we count on you to participate. And when we ask you, would you be willing to give a talk, to say, sure, gladly. Now let me go to our first speaker. That's my pleasure. That's Bernd Finkbeiner. It is really my great pleasure to introduce him. Bernd is actually one of the first. I met him when I was a student in Saarbrücken. He was barely a professor himself. He just finished his PhD. So I'm kind of very excited that like now, after all these years, we meet almost in Berkeley. And shame that it's not in person, but it's virtual. So Bernd finished PhD nearby in Stanford with Zohar Mana, and ever since that his research was reactive synthesis, runtime verification, hyperproperties. Bernd is right now at CISPA, which is in Saarbrücken, and also when it comes to the recognitions, you probably have heard that he received this very large ERC award. That's really big money grant, and he received the best paper award at ICALP. But also what is impressive is that the number of students that he graduated. He already graduated. He's such a young professor, and he's already academic grandfather. His first student already is professor, and he already has students. So Bernd, we couldn't find a better person to talk about reactive synthesis, and we are really excited that you agreed to give this talk. Thank you. And also maybe one technicality is I will monitor chats. So if you have any questions, please just write it, and then I will stop there and write questions. Or I will also look if someone is raising hand, if you prefer to raise hand. Thank you, Bernd.
All right. Thanks very much, Ruzika, for this really nice introduction. You failed to mention that we didn't just teach together, but also did a lot of great research together, right? Yeah, thanks very much for the introduction. Thanks very much to the organizers for having me. This is a great pleasure to talk with you about synthesis. I'm using a setup that I normally use for teaching, and that I have actually not tried out before for a talk like this. So, you know, if you can't read anything or anything else goes wrong, let me know. Also, let's make this as interactive as possible. I'm not sure if I can see the chat really, so I'll rely on Rosita to read if there's something going on the chat. But I can hear you, so if you just jump in, I think that works fine. Yeah, so reactive synthesis is, of course, an intriguing topic. It's an old topic, right? It has been around for more than 60 years. And, you know, it has shifted in many ways from a purely theoretical endeavor to something that has practical applications. And yet there are so many questions still open, even about the most fundamental things. So I was thinking I can't really do justice today to the full sort of area, of course, but I will do the following. I will start with a brief history. This is just to do justice to the fact that there is 60 years of work. So I just want to step through the highlights, what most people will think of when they think of reactive synthesis. Then there's a part where we talk about the basic algorithms, which are the established things you can use in order to build a reactive synthesis algorithm, right? Just the basics, not at too much depth. And then I'll have a third part, which I called challenges. And these are really just three areas that I think are extremely promising, and where there is already quite some research, of course, but that are definitely far from being resolved. So I think these might be three topics that could be fun to discuss also during the Simons Institute. So I'm guessing, you know, I'll have some ideas, of course, to share on these three areas, but this is not, you know, final in any way. All right, so let's get into it and a brief history of reactive synthesis. And there can't be a talk about reactive synthesis without Alonzo Church. So let's go to Alonzo Church and Church's problem, which was initiated in the 1950s, but it is unchanged until today and is sort of synonymous with the reactive synthesis problem. So suppose you have a specification that talks about sequences of valuations of input and output variables. So these are infinite sequences. So we're talking about a reactive system, and it gets in an infinite sequence of inputs and outputs an infinite sequence of outputs. And there is a specification that relates the two. For example, a S1S formula or any other sequential logic. Now, our task is to construct an implementation that is a finite state machine represented, for example, as a circuit that translates the inputs into outputs such that the given specification is correct. Okay, a classic example here would be an arbiter, right? So you have requests from two clients, R1 and R2, and you're supposed to produce grants, G1 and G2. And the typical requirements are that you want mutual exclusion. So there are never two grants, G1 and G2 at the same time. And at the same time, you have responsiveness. So every request Ri is eventually followed by a grant Gi. Okay, so obviously this is a specification that can be implemented, and you might do so with a finite state machine that, say, starts in this state, and as long as there is no request, it just stays there. If a request R1 comes in, then it goes to a new state where it actually outputs the first grant. grant G1, right? And as long as new requests only for the first client come in, it stays there and keeps outputting the first grant. Likewise, if we're in the initial state and the request for the second client comes in, then we just start outputting grants for the second client. And now, if the two requests come in at the same time, then things get more interesting. So you might, for example, go back and forth between giving out the first grant and the second grant, and back and forth until you're done satisfying all requests. So when you read as a human this specification, then you might immediately think of a finite state machine like this, which is a correct implementation of the given specification. Now, of course, when you do synthesis, one of the basic facts of life is that you get what you specified, not necessarily more or less. So there's a totally acceptable alternative solution, which you see here, which only has two states and simply goes back and forth between giving out the first grant and the second grant, completely ignoring what requests come in. Why is this a legitimate solution? Well, it does satisfy mutual exclusion and response, right? If there were to come a request, it would eventually be answered by a grant. The fact that we also have in mind the requirement that you only give out grants if there was actually a request that justifies that is not specified in the specification, and therefore you have no guarantee that the implementation generated by the synthesis will have such extra properties. Okay, now Church's problem was solved pretty quickly. So the original solution due to Büchi and Landweber translated the synthesis problem into a game. So we have a player 0 that's responsible for the outputs and a player 1 that's responsible for the inputs. And we're just looking at the sequence of inputs and outputs that are generated by letting those two players pick outputs and inputs in turn. Now, our player 0 wins the game if the sequence of inputs and outputs satisfies the specification. Otherwise, player 1 wins the game. So really, we're interested in a winning strategy for player 0. If such a strategy exists, then that defines a valid implementation. And dually, if player 1 wins, then there does not exist a winning, there does not exist an implementation for our specification. Another early solution is Automata. So you can view the same problem in Automata theoretic terms by looking at such winning strategies. Such winning strategies are trees. So you look at it from the perspective of player 0. Player 0 needs to pick the outputs in response to the inputs. So this is an infinite tree that branches according to the possible inputs. So in this example here, it's there's only one bit that is either set or not. So the empty set means 0. The set containing I means the variable I is set to 1. So we're looking at the infinite tree that branches according to these inputs. And in each node of the tree, we see the value of the strategy. That is what player 0 is going to output in response to the inputs seen so far. So the existence of such a strategy corresponds to player 0 winning the game. And we can build a tree automaton that accepts all the winning strategies. So this means that if we check the emptiness of that tree automaton, that is equivalent to determining who wins the synthesis game. There is, in fact, a one-to-one correspondence in the sense that checking emptiness of tree automata can be, again, seen as a game, namely the emptiness game. And so we can translate to tree automata and back again. The relevance for synthesis is that now we have a mechanism to represent all the solutions. And that, of course, is useful if we have additional requirements on the solutions. We can transform this representation, which gives us more flexibility as in the game representation. Okay, now this early work was based on logics like S1S, which are, of course, let's say, impractical in the sense that there is no elementary translation to automata, but this changed with LTL. So in the 80s, with logics like LTL that were useful in verification, the corresponding synthesis problem got, let's say, a lot more interesting because it's much more feasible to translate the logic into automata. So this is work by Amir Pneli, of course, also by Amir and Roni Rosner came another very interesting generalization of the problem, which is the synthesis of distributed systems. So in Church's problem, you look at one circuit that is supposed to satisfy the specification. In the distributed version of the problem, you additionally provide a target architecture for your system. So you have more than one process, and you have an architecture that regulates how these processes can communicate with each other. And now the synthesis problem is no longer to just find this one circuit, but rather find a solution for each of the processes in the architecture, such that when you combine them again, you have a solution that satisfies the given specification. Now, looking at this variation of the problem makes it a lot harder. And the reason that synthesizing distributed systems is so much more difficult than synthesizing circuits is that you're working with partial observation. Let's say you have a simple architecture with two processes, process 1 and process 2. Process 1 reads in an input from the environment, let's call that X, and then it produces Y, which is then the input that goes into process 2, who then in turn produces a variable Z. Now, what this architecture means is that process 2 does not directly know about X. It only knows about X in as much as it can deduce from seeing Y. And this means that the decisions process 2 makes must not depend on X directly. It may only depend on what's visible of that in Y. So if we again look at the strategy tree of the overall system, then that, of course, branches according to the inputs of the system, so according to the values of X. And then in each node, it would give us the values of all the variables, including Y and Z. And you might have a situation where two nodes have different values of Z, like 0 here and 1 there. But the history that takes you to those two nodes has the same values of Y, right? So in the first step, we saw Y is 1, and then here we see Y is 0, here and also there. So our process 2 can't really distinguish whether it is in this node or in that node, right? Only process 1 knows whether we are here or there because there is a difference visible in the X. But since there is no difference visible in the Y, it's not legal to have different values of Z in those two nodes. So the only consistent, consistent strategy would have Z equals 1 here and there, or Z equals 0 in both cases, but in any case, it needs to have the same value. So this additional consistency requirement makes the problem very hard. And in fact, there's a long history of results that show that the distributed synthesis problem is decidable for specific architectures. The original one from Pneli and Rosner was the pipeline. So you have an environment that produces some information that goes into the first process, and then that gets handed over to the second process. But the important point is that the second process does not have new information. It only gets a subset of the information that the first process got, and so forth. So if the architecture is hierarchical in this sense, then the synthesis problem is decidable. There is a result by Kupferman and Bardi that generalized this to rings. So you can have ring architectures that also have this property that the information is entered at one particular process in the ring. Then we did a small generalization of this to weakly ordered architectures, which means that as long there is a weak order that ranks the processes in terms of their informedness, the problem stays decidable. And for the synchronous systems, this is already the borderline. Everything beyond that becomes undecidable. So in the original work by Rosen and Moedi, there was already this architecture that has two independent processes, and that is the master architecture that has an undecidable synthesis problem. There has been quite some work on asynchronous systems, so systems where you don't have a common clock, meaning that the state changes happen in lockstep, but rather there's independent computation going on. And in that area, there are also a number of interesting decidability results. In particular, there's the one by Mushol and Walukiewicz, which tells us that synthesizing systems that have an acyclic communication architecture. So, for example, two processes that talk to each other, or a star architecture where you have a process in the middle that talks to many other processes. These are all examples for distributed systems that are decidable in the setting of asynchronous systems. So unlike for synchronous systems, there is no clear boundary yet where the decidability lies. We only have these examples for decidable architectures. Okay, so the bottom line of this story about distributed systems is that there is a large class of architectures for which synthesis is decidable in principle, because you can build a tree automaton that represents all solutions, and then you just need to check that tree automaton for emptiness. However, typically that tree automaton is huge. So for an architecture with n components, you need n+1 exponentially many states. So a tower of n+1 exponents. So the complexity is non-elementary. And of course, in general, the problem is undecidable. So this means that, at this point of the discussion, there's quite some doubt if this leads anywhere, right? Because we have a problem that's in general undecidable, but where it is decidable, it has this horrendous complexity. So you might question whether this is really solvable in practice. And at this point in the story, I think there is one event that gave people a lot of hope, and that was the synthesis of the AMBA bus protocol in 2007. Hi, Nir, I didn't notice you there until now. So yes, by Nir and quite a few others. So I think what is so encouraging about this is that it was the first time a real system got synthesized. I mean, at least something that is being used in industry. You probably have some version of this protocol on your cell phone. So clearly, synthesis is not just a toy, right? It can do something useful. Now, the AMBA bus protocol is a high-performance on-chip bus. You have something like 16 masters and clients that communicate to each other across the bus. And the bus got specified using I think in the original work, 12 guarantees. So these are temporal requirements of the form that a new access does not start until the current master releases the bus. And the bus arbiter only needed to satisfy these guarantees under certain assumptions on the behavior of the clients. So for example, that the clients indicate infinitely often that they have finished processing the data and are releasing the bus again. So the reason why it suddenly became possible to synthesize something realistic like this was, at least to a large extent, the discovery of GR1. So the general reactivity one fragment of LTL consists of specifications of this form. So you have a conjunction of assumptions and a conjunction of guarantees, and it is restricted what you can express in these assumptions and guarantees. So you can state what needs to happen initially with initialization properties, which are just state formulas. Then you have safety properties that describe the rules of the game, right? So they are of the form, if some condition holds, then something else needs to hold in the next step. And lastly, you have liveness properties of this form, something needs to happen infinitely often. And now you're restricted that you have assumptions of this form and guarantees of this form, and you're looking at an implication between such a conjunction of assumptions and guarantees. Now, the great thing here is that this can actually be checked in exponential time. Near would probably say in polynomial time, because if you like, you can measure the complexity, of course, in the size of the state graph, which is again exponential in the size of the formula. But even if you say this is exponential, then I think it's a great result, because I mean, after all, we're coming from non-elementary, or in the case of full LTL, at least doubly exponential, down to an exponential time algorithm. And this, it turned out in a way that it was still a useful specification. So I think this is the reason why synthesis suddenly got adopted also in robotics and many areas that are not traditionally connected, let's say, to formal methods or theory, right? Because there was an algorithm with which you could actually do things. Okay, another development that, in my opinion, changed the game was bounded synthesis. So in general, in synthesis, we ask the question if there is, is there an implementation that satisfies the specification? And by implementation, we mean a finite state representation. Now, in bounded synthesis, you ask, is there an implementation with no more than n states? Which in a way is a small difference, because you're looking for a finite implementation in the first place. But the difference, of course, is that now you have this parameter n that gives you a maximum size that you need to look at. Now, the immediate implication of this change of perspective is that everything becomes decidable, because you have an upper bound up to which you need to search. And of course, now you have a measure on the output rather than on the input. And it turns out that this measure on the output is much more favorable, because you can solve pretty much any synthesis problem in NP. In NP in this bound, right? Not in the specification. But this means that the one process architectures in Church's original problem, or which have doubly exponential complexity in the LTL specification, or the pipeline architectures, which have non-elementary complexity in the specification, and even Pnelli and Rosner's independent processes, which are undecidable, they all drop to NP. Now, NP is, of course, not the most scalable complexity you might wish for, but it still means that no matter what specification and architecture you're coming from, as long as your solution is reasonably small, you have a way of finding it. So this, I think, changes the picture from something that looks impossible to something that looks a bit tricky in terms of scalability, but definitely solvable. Okay, what else happened? So I think a lot of improvements in reasoning methods happened. So there's, of course, the big ticket result that parity games, for which we have a whole range of algorithms that run in exponential time, they got solved in quasi-polynomial time. We now have something like 4 very similar algorithms that solve parity games in quasi-polynomial time. And of course, solving parity games is sort of the key problem in synthesis. Now, it turned out that these algorithms, at least so far, aren't that useful in practice. They tend to be among the slowest algorithms we have, at least in practice. So the impact of this was not that earth-shattering as you might have hoped for. What was much more of an impact was actually simply better engineering. So in the last years, a new crop of tools and also algorithms came around that just work much better. So I mentioned here Strix, a tool developed in Munich, which performs amazingly well. Even though I wouldn't say that it's not comparable in its theoretical shift to the new parity game algorithms, but it's just very clever in many aspects. For example, it treats subformula separately, exploits similarities between subformulas and many ideas of this nature. But better engineering really changed things a lot. And then there was a lot of progress in constraint solving techniques that are helpful in synthesis. In particular, the sort of set solving had improved earlier, right? But QBF and DQBF solving really got better in the last few years, let's say DQBF solving in the last 5 years. And that also helped enormously. I'm pointing here to the Under Tentrop's thesis because that's a recent thesis on the topic if you just want to track these developments. Okay, so where are we now? 2 years ago, we looked at, again, a rather elaborate case study. So this is it's the Synthroids game. It's an arcade game. It's a handheld device that has an LED screen, and it has an FPGA on the back and all kinds of sensors, acceleration sensors, and so forth. And what you can do with this is play a game where you're flying on a spaceship and there are all sorts of enemies coming at you from all directions. And then you can look at the situation in multiple views. You have like a radar screen, and then you can look through the window, and all this is displayed to you on this LED display. So it is run very efficiently on an FPGA, and the code for this FPGA consists of 24 different modules that interact with a base system with another, say, 40 functions. So this is a pretty elaborate type of implementation that needs to keep track of a lot of data, for example, the positions of the different aircraft and so forth. And this was actually not hard to synthesize. using the latest synthesis algorithm. Of course, also concepts like compositionality and program synthesis that I'll talk about in the third part today. But to me, that suggests that we have reached a point where you can actually develop systems with synthesis. So this is a very nicely developed system. If you look at the specification, that's much nicer compared to a manually written code. It's certainly something that you can also develop manually. It's not that the synthesis can do something that you couldn't do as a human programmer, but of course, you have to guarantee that all your properties are actually true on this system, and it has quite a few aspects that human programmers would consider tricky. For example, the correct timing of the signals that go onto the screen, as the different LEDs on the screen are activated. All right. So this is my short history. I will now start going through some of the basic algorithms that are in play here. Okay, so the basic story for synthesizing systems from LTL formulas goes like this. You start with the formula, then translate it into a automaton. Let's say a non-deterministic Büchi automaton, then you determinize this automaton, you get a deterministic automaton, say a deterministic parity automaton. Then you separate out the choice of the inputs and the outputs. That is, you turn this automaton into a game. This is a parity game, and now you just see whether player 0 wins the game. If so, the winning strategy for player 0 is your solution. Let's say our specification is a simple response property. So globally, whenever there's a request, I want to see eventually a grant. Then you might translate this into a deterministic parity automaton. So this parity automaton has two states. One where you say everything is good, nothing is to do. So you stay in this state if either nothing happens or you give out a grant, or there's a request and immediately also a grant, and you just stay here. When there's a request, you go into the second state where you're waiting for a grant. So you stay here while nothing happens or further requests happen, but no grant. And when the grant happens, then you go back to this initial state. So this is labeled with parity colors 2 and 1. So the automaton accepts if the highest color occurring infinitely often is even. So essentially, if you come back to the initial state infinitely often. Okay, so we take this automaton and translate it into a game. So we have our two players, right? So we start here in the initial state of the automaton. And then we can decide whether we do nothing or give out a grant. Either way, we stay in state P. And now the environment can either also do nothing, that is send no request, in which case we go back to the upper state, or it can send out a request. So if our implementation chose not to put out a grant, then we go into queue and wait for this to happen. And now here from queue, our implementation has two options. It can either do nothing, that is not give out a grant, in which case we go to this state up here, right? So we stay in queue in the automaton and just output nothing. So we go back and forth until we actually give out a grant. Or it can choose to give out a grant, in which case we go back to the original state, to P. So we have taken the automaton and turned it into a game that just alternates between the two players and mimics what happens in the automaton based on the choices of the two players. Now, there's a winning strategy for our implementation. It can, for example, do nothing initially, which takes it here. Now, the environment might respond by also not producing a request, in which case we simply go back, or by producing a request, in which case we go down here. And now our winning strategy might actually choose to answer this request with a grant, in which case we come back to the original state. So we have one winning strategy for this game, and we can turn this winning strategy into an implementation that then just does what our strategy suggests, namely, while there is no request, just do nothing. But if there's a request, go here and issue a grant, and then go back to the original state. Okay, now a quick question, why do we use deterministic parity automata here? The first question is, why do we need deterministic automata? Well, the problem if you were to use non-deterministic automata is that you might get rejecting runs of the automaton even if you run the automaton on an accepted sequence, right? Because there's another run of the non-deterministic automaton that accepts the sequence. And that might penalize our player zero, because it might be the case that player zero loses a play just because we end up in the wrong run of the non-deterministic automaton, not because the player did something wrong. So, for example, if you have a disjunction and one says eventually we have globally that the input is true and in the next step the output is true, or we have infinitely often that the input is false and in the next step the output is false, then player zero has a winning strategy, namely simply to repeat what the input at the output. But if we would ask our player to pick one of the disjuncts, then it would not know which one to pick, because it depends on the behavior of the environment. So since we don't want to burden one of our two players with making this, choosing the disjunct on which to win, we simply eliminate the disjunction in the automaton and look at the deterministic automaton. Okay, and the other question, of course, why not deterministic Büchi automata? Well, because if we start with LTL, then deterministic Büchi automata would not be strong enough to express all LTL properties. So we just go to deterministic parity automata. Okay, now the complexity of this, going from LTL to a non-deterministic Büchi automaton, is exponential. Going from the non-deterministic Büchi automaton to the deterministic parity automaton is again exponential. So your number of states becomes doubly exponential, and you need an exponential number of colors in the parity automaton as a result. Now, going from the deterministic parity automaton to the parity game is just a syntactic transformation where we separate the two players, so that doesn't affect the size. But then we need to resolve the, we need to solve the resulting parity game, which is polynomial in the number of states, and either if you take the one of the classic algorithms, exponential in the number of colors, or even less so. But in any case, because the number of states is already doubly exponential, you end up with a doubly exponential cost. Interestingly, independently of the precise complexity of the parity game algorithm, because it's the complexity really is dominated by the number of states. So that may be one reason why the new parity game algorithms don't help this much, because the complexity really lies in the number of states rather than the colors. Okay, now what people are usually really worried about in this construction is actually not so much the two exponents, but this particular step, going from non-deterministic Büchi automata to deterministic parity automata. Well, the standard way to go from here to there is via Safra's construction, which is infamous because it's not only expensive, but also really difficult to implement, for example, in a symbolic algorithm. So because of that, there are a number of Safra-less constructions. So the first obvious way is to just bypass the non-deterministic automata. So you use a construction that takes you from the LTL formula directly to the deterministic parity automaton. This is, for example, done in Strix. So there's a direct construction that is very clever in the use of the subformulas of LTL, and furthermore completely bypasses this need for Safra's construction. Another option is to go directly from the LTL formula, not to a parity automaton, but rather to a safety automaton. Safety automata are much easier to handle, in particular symbolically, than parity automata. But of course, you can't recognize the same language as an LTL formula with a safety automaton. But what you can do is you can approximate the language with the safety automaton. So there is a construction that gives you a family of safety automata that has the guarantee that eventually you will have a safety automaton that includes your solution, assuming that there is a solution for the original LTL formula. So you can think of that as if you have eventually P, then you just start with an automaton that waits 1 step, then 2 steps, then 3 steps, and 4 steps. If there is a finite solution that will accomplish P in n steps, then the nth automaton will catch that solution. Okay, so by going through this sequence of more and more precise safety automata, all you have to do in each iteration is solve a safety game. All right.
Bernd, can I ask a question?
Oh, yes, please.
So the old, the three automata-based mention of representing all possible solutions to some subset of games that you mentioned much earlier in your history. That one has an advantage in the sense that if I have access to all possible solutions, I can try to do extra things with them. If I'm interested in a particular solution, I can try to pick it out of the bunch, etc. So these three methods that you just highlighted, can you say something in general about their advantages and disadvantages in terms of if I had an interest in enumerating solutions, what would they look like? I don't know if my question is good enough in something.
Okay, you're a number of steps ahead in the story, but it's an outstanding question, of course. I mean, I guess you're asking, we don't want just any solution. Usually, we want a good solution. And if I have a tree automaton, then I can delay the problem until I check the emptiness of the tree automaton to pick the one solution that I want. Here in these approaches, you may have to do this much earlier. So in particular, in this construction, what you do is you look at the subformulas and you solve the games represented by these subformulas individually, and then you try to combine these solutions into a big solution. So you do that for efficiency because you may not even be able to construct the full automaton in one go, but you can already build automata for the subformulas, so you get started with what you have. But of course, it's impossible at this stage to do a global optimization. You do a local optimization, and then you do strategy iteration to adapt until you have a solution that works globally. So indeed, it's much more difficult to add extra things like minimality or so into the consideration. However, these tools don't do so badly on the quality. And the reason is that this compositional approach gives you a reasonably small solution. It often actually does better than the global solution, which does a full product construction where you lose sight of things. Here you have a much more manageable state space to optimize on. And then, of course, they do a post optimization and again, try to optimize the solution they have afterwards. Now, the approach that approximates things with the safety automaton actually goes into the direction of minimality, because in my example with eventually P, if you bound the number of steps until you hit the P, that sort of forces you into a more efficient solution, right? You don't allow to take 25 steps if there's also a solution that only takes 5 steps. So that already goes in the solution, but it also does not have a guarantee that, for example, your state space is minimal. It just has this optimization of the reactivity behavior. So all in all, I think none of these solutions are targeted towards producing optimal solutions. Bounded synthesis is in a way much better than that, because there you optimize a global bound. But it turns out that they do surprisingly well in practice, because I think that this is how a human would approach the thing, and that gives you a reasonably good solution. Whereas having a full product is just scary. All right. Yeah, Nir, this is again for you. The GR1 specifications show their advantage here. So you remember we had this restriction to the specifications where you have a conjunction of assumptions and a conjunction of guarantees, and they are restricted to safety properties of this form and these liveness properties of that form. So infinitely often something happens. Now, the safety properties of this form lead actually to the exponential state space, because you need to keep track of the activated formulas. The formulas where the phi has become true, and you now need to make good on the promise of C. But the real magic happens on the liveness properties. Because of their special form, you get a parity game with just 3 colors. And this I will show you on the next slide. So if you have a formula of this form, where you say infinitely often A1 and infinitely often A2 and so forth is my assumption, and then I have infinitely often G1 and infinitely often G2 and so forth are my guarantees, then I can implement this in a game that has an outer loop and an inner loop. So this is an inner loop, and the outer loop steps through the guarantees. So it waits for the first guarantee to become true, then we go to the second guarantee, and so forth, until we have stepped through all the guarantees, and then we go back a full circle. So if we go infinitely often through the full circle, then we make good on all guarantees. Therefore, the game is won by player 0 in that case. Now, the inner loops just step through the assumptions. So we wait for assumption A1, then assumption A2, and so forth until we hit assumption AM. And then we go back. And it might now happen that we step through the assumptions infinitely often before we make progress on the guarantees. So if this happens, then we see an odd color infinitely often, right? So player 1 wins. And now lastly, there are these mini loops where we just wait for the next assumption to become true. And well, if we get stuck in one of those loops, then we have color 0, and it's player 0 who wins, right? So we have the 3 colors, color 0 to wait for the next assumption, color 1 to wait for the next guarantee, and color 2 if we complete the full circle. And this is all we need to resolve the GR1 synthesis problem. So we have an exponential game graph, but we only have 3 colors. So this indeed can be solved very efficiently. Okay. The trick in many cases is to solve these games not explicitly but rather symbolically. Although it's not quite clear whether symbolic approaches really outperform explicit state approaches. The idea of doing this symbolically is very simple. So you have a symbolic transition relation, and then you define a controllable predecessor, which here from the perspective of player 1 says that there is an there is an input by player 1 such that for all inputs by player 0, I have a successor state in my given set, right? So this lets me backpropagate by 1 step what player 1 can enforce in the game. And if you build a fixed point based on this controllable predecessor, then you get all the states where player 1 wins the game. And this is exactly the unsafe region of the game from the perspective of player 0. Okay, you can implement this construction, for example, with BDDs. But as I said, it's not completely clear whether symbolic approaches are really superior to explicit state approaches here. So definitely part of the success story of GR1 was that it had a BDD-based implementation. If you look at the recent SyntComp results, then indeed there are still BDD-based solvers that do well, but Strix, which starts winning more and more categories, is an explicit state approach. So clearly, BDDs, AIGs, and also SAT and increasingly QBF seem to do well on circuits with large input vectors. But if you have a specification that can be decomposed well, and you can solve the reasonably small subgames efficiently, then it seems that explicit state algorithms are really the way to go here. Okay, so I want to get started with bounded synthesis, but Rosita, when would be a good time to take a break? Is that now a good time, or should we go on for a little bit further?
I see some nodding, so let's then take a 5-minute coffee break. Before we go, are there any last-minute questions for Bernd before he goes to bounded synthesis? Okay, so let's then take it a break. We'll talk later.
All right. So I guess 5 minutes?
Yes, let's start at whatever time in time zone you are, guys, at 35.
Sounds good. Sounds good to everybody.
So you got a lot of snow, Rujitsa, right?
You should see pictures. Quite a lot of snow. How are things in Canada?
Cold, but no snow.
For us, cold will start in a couple. For us, first we had the real cold, like almost like, well, I know that it's not Canadian real cold, but real feel was minus 24 Celsius, so almost.
Oh, really?
Yeah, and then we got snow, and now we're getting snow again. Yeah. Ben, before we start, since you're here, I actually got several questions about your slides and techniques that you're using. You have to, before you're allowed to continue with the talk, you need to tell us what you're using. And because I got even, okay, I won't tell from whom, but the question was like, it really makes me much more involved, actually, maybe because it feels more like a real talk. So there were really a couple of people saying that this is great. So maybe you can tell us what is technique that you're using, because we all want to use that now.
It's absolutely impressive, Ben. You made our day. You know, people might think that it's Simon's Institute that had this incredible technology, you know, but you should tell us also.
Yeah.
All right. Yeah, I'm very glad you say that, because I was a little bit worried that it's not quite as sharp as usual screen sharing. So Zoom optimizes somewhat differently if you have a video rather than a static image like a slide. But other than that, this is a tool called OBS that lets you combine different video sources. So in this case, my keynote slides together with the image from the camera. And essentially, this is a green screen effect. I mean, normally green means you stand in front of a green screen and then that's replaced with an image. Here, my slide, I mean, the color white in my slides is made transparent, so I can stand behind the slides. So I also think this is much nicer in teaching, because you don't have to choose whether you look at the slides or at the person. You can look at it at the same time. So I recommend it for that. Okay, but now back to more important.
How did you download it? So don't go that fast. So where do you download it? So OBS. So where is it?
OBS is an open source tool. You can. There you go. Thanks, Anna.
All right.
Yes.
Thanks, Anna.
Okay, and now to the slides.
You can go.
Okay. Yes, so bounded synthesis solves, of course, in principle, the same problem. We have an LTL specification, and we want to find an implementation. What we do is we translate the LTL formula into an automaton, this time into a universal Corbusier automaton. I'll explain that in a moment. You don't actually have to go down to a deterministic automaton. It suffices to build a universal automaton, which is actually exponentially cheaper than going to the deterministic automaton. And then you build a constraint system such that any solution to the constraint system is a solution for your original LTL formula. Now, if you can do this translation from here to there without losing anything, but then you get a constraint system over the natural numbers that is not in general decidable. So what you do is you introduce a bound. So your constraint system actually refers to a bounded domain, and then you can solve the constraint system up to that bound in NP. So quickly, how does this work with universal Corbusier automata? They're the dual of non-deterministic Bussier automata. So you can, for example, generate them by building the non-deterministic automaton for the negated formula and then pretending the non-deterministic automaton you get is actually a universal automaton. So it accepts a sequence if all runs of the automaton satisfy the Corbusier condition. So in this example, where we want to just check if our arbiter works correctly, so it does not have two grants at the same time, and every request is eventually answered by a grant, we would have these three states: the green state, which we start out in, and that would stay active throughout the sequence. It would fail to accept if two grants came in at the same time. But if there's just a request one or request two, then it just launches into one of the successor states. So let's say if there's R1, then we stay active in green, and then additionally, we go into the blue state. If we also have request two, then on top of that, we also go into the red state. And there we have rejecting states. So we are only allowed to stay there finitely long. So we stay there, let's say in the blue state, as long as it takes until we see grant one. So if after a finite number of steps we see grant one, then we eventually are done here. So we satisfy the acceptance condition. Likewise here, we wait for grant two. We stay here until grant two happens. If that happens after a finite number of steps, then we're done. But if we wait here forever, then that would violate the Kobe condition. Okay. Now, an implementation is correct if every execution satisfies the LTL formula. And this is the case if and only if the product of the implementation and this automaton has the property that on all paths, the Kobe condition is satisfied. So let's say we have this rather simplistic implementation where we just go back and forth between giving out the first grant and the second grant and completely ignoring the input. This is a correct implementation of our LTL formula. So in order to check that this is the case, we look at the product between the solution and the universal Kobe automaton. This is this graph. And now we just make sure that in this product, we don't actually stay in a rejecting state infinitely long. And as you can see, this is not the case because, I mean, there is this loop here that loops between the two copies of the green state, right? Because we go back and forth between 1 and 2 here, and we have a self loop on the green state, but this is fine because the green state is not a rejecting state. If we see a request and go into one of the blue states, say, then it only takes one step until we get stuck, simply because in our implementation, it takes at most 2 steps until we see the respective grant. So it does not take more than 2 consecutive steps inside the blue or symmetrically inside the red state until this thread in our product reaches an end. So this product graph is an actual proof that this implementation is correct with respect to our specification, i.e. it is accepted by the automaton. Now, what we look for are annotated implementations that carry the argument why the product will not have infinitely many visits to rejecting states in them. And for that purpose, we just look in the product and annotate each state in the product with the number of visits that that a path to the state has seen of rejecting states. So, for example, here the number is 0. We have never been in a rejecting state. Likewise, in the second green state, I mean, we have gotten back and forth as long as we wanted between those 2 states, but the total number of visits to rejecting states is 0. Now, here, the number is 1 because we come from 0, and now we visit a rejecting state, the blue one, so the number is 1. And down here, it's 2, but there's no successor, so it never gets higher than 2. And likewise, over here, down here, the number is 1 because we come from the green state and are now for once in the rejecting state. So this is the first visit, and up here, the number is 2. But it never gets higher than 2. So we put this annotation directly on the implementation. So we indicate for each partner in the product, in this case, the blue, the green, and the red state, what is the number that you would put on the state in the product that limits the number of visits you have seen on any path that leads to this node in the product. So by having this annotation, we can, of course, quickly verify that this annotation is correct. We just check, okay, coming from a blue state, is there a way to go to another blue state, say, and further increasing the counter? No, there is not, because here I am already in a state where the grand one is given, and I can't stay in a blue state because I can only stay there if the grand one is false. So by searching for an implementation together with the annotation that proves that it's a correct implementation, we solve the synthesis problem. So this is exactly what happens in the constraint system. So we have a representation of the solution, that is of the finite state machine, that just specifies how the implementation behaves. So we use a finite subset of the natural numbers to encode the states, then have a labeling that is a function that maps this set of states to Boolean values representing the value of a particular output variable. And then we have transitions. So for each possible input, we have a transition. I mean, we have a function that maps states to states, indicating what would be the successor state if that particular input were to happen. And then the annotation is represented again by functions. So we have a Boolean function that indicates for each state of the implementation and each state Q of the automaton, if they do happen in combination. And then we have a rejecting bound that, well, simply indicates this bound in the annotation. And then we add a lot of constraints that just state that this particular annotation is correct. So you would start by saying, okay, the state 0, the initial state, must be labeled with the green state, right? Because our automaton starts in the green state, so the initial state of the implementation must carry the green state. And if you are in a green state, then no matter what input comes, you're going to stay in the green state. So that means applying the transition function once will lead you to a state where the green state is again present. This is simply because in our automaton, there is a self loop on the green state. We can't escape the green state. Likewise, if we're in the green state and a request comes in, then the successor must be labeled with blue, right? Because the automaton says if you're in green and you see request 1, then you must be in blue. So these types of constraints enforce that the labeling is correct with respect to the transitions of the automaton. And then we also have constraints that make sure that the numbers are correct. So if you are in a green state that is in a not rejecting state, then the successor can't be labeled with a smaller number than the present state. This just means that whatever visits to rejecting states you had previously, it cannot become lower on successor states. So it must be greater or equal. But if you are in a rejecting state, such as a blue state, then you have one more visit to a rejecting state, so that number must go up. So therefore, in those situations, you have a strictly greater than condition, and so forth. So with these constraints, we ensure that the annotation is indeed correct. So if we have a solution to our constraint system, then that is a transition system that would be accepted by the automaton and therefore would necessarily satisfy the LTL formula. Now, I've shown you this constraint system here using uninterpreted functions. So you could absolutely give this to an SMT solver and ask the SMT solver to generate the solution. What we typically do is code it down further to SAT QBF or DQBF. So the reason obviously being that these low-level solvers are typically more efficient. And they also give us a choice in how symbolic the solution is going to be computed. So essentially, if you go down to SAT, then everything becomes explicit. You have an explicit table for all these different functions, and you have a Boolean value that indicates whether or not a certain transition is possible. If you use QBF, then you can make use of for all exists constructions that allow you to, rather than enumerate the values of a function, just state the existence of a function, namely for all arguments x, there is f of x, namely there is a y, right? But it only allows you to do that in a limited way because you cannot use the same function twice. You can only use this encoding if you have functions that appear in the constraints only once. So in the synthesis, this corresponds to a symbolic treatment of inputs. You can say that for all inputs, there must be a successor in the transition system, but you don't have to enumerate the solutions, you can quantify over them. And so it continues. So with DQBF, you can actually describe all the functions in the constraint system by quantifiers. And this means that at least in the representation of the constraint system, you never have to explicitly enumerate the states, neither of the implementation nor of the specification automaton. So this is the most concise representation of the problem. It's much smaller than the SAT encoding, but of course the DQBF is a more difficult constraint solving problem. So it used to be that QBF was the most effective way to solve this type of problem, but in the last 2-3 years, DQBF has actually been catching up. And this is very nice because this is the most elegant formulation of the constraints that leaves the most liberties sort of to the solver. So it's very nice that there are now DQBF solvers that seem to be able to exploit that. Okay, so bounded synthesis is actually a decision procedure. I mean, I'm not sure if that was obvious because the way I explained the story was, of course, that you look for a solution that is an implementation, and you incrementally increase the bound that you set on the size of that solution. So in that sense, it's just a model generation, right? You increase and increase, and potentially you will never find an implementation because none exists. But the nice property of the synthesis games is that they're determined. So if player 0 does not have a winning strategy, then player 1 has a winning strategy. So rather than just looking at the game from player 0's perspective, I can simultaneously look at the game from player 1's perspective. So if the search for a solution for player 0 does not terminate, then the search for a solution of player 1 is guaranteed to terminate. So this is actually how it works. You look at the problem from both perspectives simultaneously, and then you have a guarantee that eventually you will either find an implementation or a counter strategy for the environment that makes it impossible for the system to satisfy the specification. Now, how long it may take to find either one is exactly the complexity you have from the direct game-based approach. Namely, you know that if you construct a full game, this is doubly exponential in the formula, and then there exists a positional winning strategy on this doubly exponentially large game graph. So if your bound hits a doubly exponential value in the size of the specification, then you're guaranteed that either the system or the environment will have a winning strategy. And at this point, the algorithm terminates. Now, obviously, your hope is that one of those strategies will be found much earlier than that, and indeed, that's usually the case. But in principle, you know that you will have a solution. Okay, now I want to quickly come back to Azade's question before we maybe go into the more advanced challenging areas. And so her question was, do we get good solutions essentially with all these methods? And the answer is, if you're not careful, then no. So this is a small part of the AMBA case study, just the part that regulates bursts of transmission bursts of length 4, and this was computed by Akacia, one of the early tools. And essentially, you see that this solution, I mean, there's no way to understand what this solution does. I'm just showing you the state space without the actual inputs and outputs, but still, I mean, it's very complex. Now, if you do bounded synthesis, then you at least get a solution with a minimal number of states. So this looks like this, which is, I mean, there's a much better chance to understand this than the previous solution, but it's, as it turns out, also not yet completely obvious how this solution works. So what we actually do in a refinement of this algorithm is bounded cycle synthesis. So this minimizes the number of states and additionally the number of cycles in the graph. And suddenly it looks like this. And I mean, you can now clearly see how bursts of length 4 are tracked by the implementation. So putting in these extra constraints that choose among the many possible solutions a good one pays off. So representation is that all you have to do is put in these additional constraints that enforce whatever property you would like to have for your eventual solution. And so, I mean, the particular method I'm describing here is bounded cycle synthesis, which minimizes the number of simple cycles in the graph. And this turns out to be one of those really useful parameters. So the reason is that the number of cycles in a finite state machine is up to exponential in the size of the finite state machine. So that means if you have a realizable LTL formula, then your number of states is bounded by 2 exponents, but the number of cycles may actually be triple exponential. So if you put in constraints that limit the number of states, then you box in the solutions quite a bit. But if you additionally limit the number of cycles, then you box it in exponentially stronger than if you just had limited the number of states. So you tighten the search space much more. And this seems to be one of the reasons why it's such a good idea to limit the number of cycles. It focuses the search very much, even more than just limiting the number of states. And it leads to well-structured solutions because you avoid unnecessary loops. Okay, so we have, I guess, about 30 minutes left. I mean, if you want to ask questions or make comments or so, please don't be shy.
I would like to ask a follow-up question to my question, if that's okay. So good solutions, minimal solutions, great. But what if I wanted to start to make the problem more complicated? For example, there are 2 senses in which I can do this. One, I can have extra constraints. They may be syntactic or not on what my solutions should look like. The other one is I want to try to involve the user into the loop, and they want to provide hints in some sense about the structure of the solution, etc. So still I can kind of imagine having access to all solutions could be helpful because you can restrict, and not having access to all could be hurtful. So if I wanted to go beyond this, is there any hope for these methods that are optimal because they don't represent all solutions, but can still accommodate some of this?
I mean, you're now referring to quite a big space of potential algorithms. So, I mean, I can tell you for bounded synthesis, the answer is pretty clear. You don't lose any solutions. I mean, what you're actually bounding is the size of the certificate that proves that you have a correct solution. So as long as you pick a bound such that the solution you're looking for has a certificate within that bound, then you're still fine. Now, depending on what your criteria are on the solutions, that may or may not be easily compatible. I mean, if your solution is such that it requires a huge certificate, then, well, you better introduce a second parameter and scale that differently and so forth. But in principle, that is certainly possible. Answering the same question for these, say, low-level compositional techniques you find in Strix and elsewhere is much more difficult, because of course your low-level optimizations need to be compatible with the search goal you have, and that's by no means a given upfront, right? So I think in the end, to be effective, you want to have these low-level optimizations, but you better check whether they're compatible with whatever additional constraints you put on your problem. Sorry, that was a very hand-wavy answer, but I don't think there's a general answer to this question. Maybe let me ask you back, what kind of constraints do you have in mind?
I mean, the simplest thing could be that, you know, as the user, I have some idea what the shape should be of the kind of, imagine it's kind of like the syntax of the state transition systems that you, and I'm hoping this would actually make things go faster. Not, I'm not trying to kind of be a bother in some sense, but help. And would it actually help if so think about it that in three automata terms, I could possibly kind of have defined a tree automaton that represents all things of the same shape. And then I can intersect this with the solutions, and I can get only solutions that look like this. But here, you know, this is just one example, but I completely agree with you that the question is a little too broad. It was just mostly to kind of...
No, but it's it's really an excellent point. So, I mean, okay, a variation of bounded synthesis is, for example, template-based synthesis, where you don't fix the number of states, but rather you fix the state of the shape of the graph. And so this has been, for example, very successful in building real-time controllers, where you do have a specific design pattern in mind, say the cyclic executive. The cyclic executive steps through a number of tasks in one big cycle, right? So you expect your solution to be a cycle, and the only thing that's open is in which order do you step through the different tasks and what deadlines do you set, right? So templates of this form make a huge difference, right? First of all, they let you solve problems that would otherwise be completely out of reach because the search space is too small. And second of all, you get solutions that make sense because they fit a particular design pattern. So I think actually this is one of the let's say the grand challenges. I think we don't have many such design patterns for finite state machines. I mean, it seems that the more abstract you become, like if you go from transition systems to real-time controllers or so, the more such things exist. But of course, you would want to like hard code such design patterns into the search, such that at least you prefer to find a solution that follows a pattern if such a pattern exists.
I have a question.
Yes, please.
Yes, please.
So one of the biggest problems in synthesis, especially of deep neural networks, is explainability. I mean, you have a complicated problem with the synthesis, and then you have no idea why it works. So this is a general problem. I mean, when I saw that first diagram that was synthesized, you had no chance to understand what's going on there. So what do you think are the key ingredients that are going to push synthesis to make it explainable, such that it gets acceptable, from the point of view of reactive synthesis?
Okay, I have a beautiful slide for this. Let me try to jump to that. Yeah, so this is what Dijkstra had to say on this. So if we ever want to compose really large programs reliably, we need a discipline such that the intellectual effort needed to understand the program does not grow more rapidly than proportional to the program length. So, I mean, he says like 2 times that this is, of course, all very loose. But I think that's a very interesting claim, because what classic synthesis algorithms do is they work on the product graph. If you have multiple components and you analyze the program, just like verification would do in principle, right? In order to make sure that there is no bug, you look at the program, the product. And that, of course, means that even if we improve the synthesis algorithms, say that they don't generate finite state machines, but they produce the corresponding code or so, there's always this product construction going on. That means that understanding that your system is correct is actually exponential in the size of the code, sort of violating Dijkstra's goal of having a linear or let's say polynomial or so dependency. And I mean, of course, Dijkstra's answer to the challenge was that you want to be compositional. So if you can look at one component at a time and convince yourself that this component does the right thing because it satisfies its specification, and because it additionally provides whatever guarantees other components might need from it, then you can understand components locally rather than looking at the product. So I think going towards compositional methods is mandatory for 2 reasons. One, because it's the only way to scale up, because you can't go to a non-elementary complexity or even just exponential complexity. You want to be linear or polynomial in the number of components, but 2, also because compositionality is our best way of making things understandable. So if you minimize the interfaces between the components, then you optimize the locality of the reasoning required to understand the component. And if unavoidable, then at least the interfaces decouple the reasoning from one component to the other. In a way, I think compositionality has much more of a chance in synthesis than it ever had in verification, because we get to pick the solution. And obviously, there are solutions that are very local, that work with a small interface between the components. And then there are other solutions that rely on a very intricate collaboration. And because we can put in additional constraints, we can force the synthesis to go towards the ones that are local and understandable. So yeah, so this is one of my.
So what you're saying is that in principle, what you can do is to put as a constraint, for example, architectural constraints. I mean, say, look, I think the system should have this kind of architecture, maybe, and so there you put some of the composition already
exactly
in the system.
I mean, you don't have to be so strict as to say you make all solutions illegal that rely on collaboration. But of course, you could just bias the search towards those solutions that are more local. And I think that's a very good strategy.
All right. Thank you very much.
How would you
Thank you.
bias this search? Would you put additional constraints or?
I'm sorry, Ružica, I didn't fully understand.
When you say bias the search, what are the standard tricks? Additional constraints or giving weights or?
Yeah, I mean, so in bounded synthesis, it always boils down to putting in a constraint that limits a certain parameter, right? So I think biasing the search means identifying the parameter and then defining a preference between the different parameters as you scale up the search. Simply because the parameters are usually of a type that, if you look for the solutions for parameter n+1, this is so much harder than the solutions for parameter n, such that you might as well forget everything you did and start from scratch for the higher parameter. But this may not be the case for all types of parameters. In other situations, it may well be worthwhile to have an incremental solution style. So I think, this is completely orthogonal, but the exciting question is, what are the right parameters?
Thank you.
All right. If there are no more burning questions, then I'll maybe go back to my challenge slides. But please, by all means, interrupt. It's probably much more exciting if you make your comments rather than me going through more slides. So I picked 3 areas that I think are both fundamental and at a stage where really something fundamental is going on, right? So I'm not sure if we have enough time to go through them, but let me get started with reactive programs. So all the techniques I mentioned in my story so far were concerned with the generation of finite state machines or transition systems. And already 10 years ago, Madhusudan said that this is actually completely wrong, because in the end, we don't want to build transition systems. Transition systems are infinite, big, not understandable. Really, what we want are programs. And programs are compact and actually the artifact we're really interested in. Now, you could, of course, argue, well, a transition system is a special type of program, but I think the criticism runs much deeper than that. So let's say if you're building a music app and you want to use synthesis for this, Ružica is smiling because she knows where I'm headed. So this is actually work by Felix Klein and Mark Santolucito, to really outstanding researchers that Ružica and I were lucky enough to supervise. So I'll describe the problem and a little bit of their solution. So let's say you want to synthesize a music app. So something like whenever you leave the app, then the control should go on pause. And whenever you resume the app, then it should start playing whatever track and track position it was on when you left the app. So if you build code for an app like that, there's actually a lot that you build on. Say there's the Android system, the Android music player library, the control interface. There is data like the chosen track and so forth. So it's not really plausible that you build the transition system that governs all these things. First of all, because you're building your system in an environment where a lot of things are already fixed. And second of all, it's not just control. I mean, there's a lot of data going on, like the music, and obviously you want to refer to that, even though it's not really part of the control problem that you're solving. So in this work, the key idea was to go to an extension from LTL to, in this case, a stream logic, a temporal stream logic, where the extension is that rather than just having atomic propositions, you have function terms and predicates in your logic, and you can talk about updates. So you can say that the control is updated with the result of the pause function, right? And you can say that without knowing what pause means. It's just a function provided by your system. So input variables refer to these streams, not necessarily Boolean, right? We have all these functions and predicates, and you specify when such updates need to happen, referring again to the values of predicates. So you can say that if a certain predicate becomes true, then something needs to happen without knowing exactly what that predicate means. So this allows you to do a functional abstraction, just like you know it from programming, right? So your control specification can refer to functions and predicates that somebody else may already have programmed. And then your synthesized solution fits in that framework. And just like if you were a human programmer doing that, you don't necessarily know all the details of the functions that you're using, but it is your job to call them correctly. And this is what you can do in such an extended logic. Now, the challenge is that you're moving actually to a different logic, because you have all these new elements, the functions and the predicates in there. And this looks very similar to LTL, but it's actually different. So in TSL, you might say something like, if eventually the predicate P of X becomes true, then you want it to eventually globally stay true on Y, where X is an input and Y is an output variable. And this is not the same thing as saying that there's a predicate PX and a predicate PY. And if eventually, I'm sorry, an atomic proposition PX and an atomic proposition PY, if eventually PX becomes true, then eventually globally PY becomes true. Why is this not the same? Well, the TSL specification is actually realizable because this is a predicate. It's the same predicate P here and there. So once I have found a value X for which the predicate is true, I can just copy that value onto Y, and then I have a value where this predicate P will remain true forever, right? Because Y is an output, and I can just pick that output. For example, I can copy the value of X. In LTL, where PX and PY are not under my control, there's always an environment that will, set PX to true at one point and PY forever to false. So the problem is different, and this is also reflected in the decidability of the problem. So while the LTL synthesis problem is always decidable, this more powerful logic that has these uninterpreted functions and predicates has an undecidable synthesis problem. However, this is clearly the synthesis problem you want to solve. So what you do is you approximate this problem that you really want to solve with one in LTL that's as close as possible. So in this case, we would take this property of the same form and just correct for all the errors that might result from the approximation in LTL. So the approximation that introduces the error is that the predicate PX and the predicate PY can somehow be chosen independently of each other. This is not the case here because they're the same predicate, just applied to different terms. So what we do is we say that, okay, we additionally put in constraints that make the two logics agree. So for example, we say that if P is true on X and we assign X to Y, then in the next step, P must be true for Y. Or if P was true for Y and we don't change the value of Y, then in the next step, the predicate P of Y must still be true. So in general, you may need an infinite number of such additional constraints in order to reflect the behavior. What we do in practice is we simply correct for the error in a refinement loop. That is, we look for spurious violations and then one by one correct these violations by adding additional constraints. So the interesting observation is that this works really well in practice. In practice, you only need a few iterations of this refinement loop in order to eliminate the spurious errors. Then apparently you have a LTL approximation that is close enough to the TSL specification so that you find a solution that works. And of course, it's conservative in the sense that if you find a solution, then that is an actual solution for the original problem. But I think logics like this could be a great starting point to actually go from finding transition systems to finding programs that work in existing architectures and that are hierarchical in the sense that you build one function at a time and then build more complex systems once you have extended your framework. But of course, there's a lot that is still missing from such a framework. So what we did there was the extension of LTL with uninterpreted functions so that we can handle function calls that have already, for functions that have already been implemented. But we don't go beyond uninterpreted functions. So there's no reasoning going on that would actually talk about the theories that occur in the programs. So I think if you want to build programs, then the essential question is, how do you combine the reasoning between the newly synthesized functionality and the parts of the program that are already there? I mean, this could be a combination of synthesis and verification, where in order to build a good new program that uses some functions, you have to carry out some analysis of the functions that are already there. But it could also be a combination of reactive synthesis and deductive synthesis, where once you have figured out how the control needs to be, a deductive synthesis approach can then build the functions that you need in order to have the correct data transformations. All right. So I think this is one of the big areas, going from transition systems to actual programs. We don't have too much time.
I think this goes also, yes. If I may, this goes also in direction of understandability. I mean, obviously, because these programs are such more higher level that it's much easier to understand them, and they are structured.
Yeah, I think understandability is a big part of the story, but it really goes beyond that. I mean, the classic version of Church's problem attempts to build the whole system in one go, right? You have one specification and you build one solution that satisfies the specification no matter what. But you don't build programs in this way. You don't start from scratch, but rather you already have some parts and then you build new parts that use what you have already built. I mean, partly that is due to understanding what you're doing, right? But partly it's also to manage complexity. You don't want to build a big system in one go. So that's a big disadvantage of these classic algorithms.
Anna, please. Anna, you have a question.
Yeah, hi. I have a question about counterexamples. So let's say, but it's also related to explainability in a way. So let's say that we want to provide more explainability by detecting more of these counterexamples from which we can learn how to improve our system. Is there any way how we can guide this counterexample search? So to say that our method would remember what counterexamples we already found and how to find counterexamples that are close to what we've seen so far, or maybe very different from what we've seen so far.
Yeah, very good question. So I think partly the answer is that the search for counterexamples really is dual to the dual version of the problem to the search for implementations. Because if you have a specification that's not realizable, then the environment has a strategy to prove this, right? To make it impossible for the system to satisfy the specification. So given that we have a specification that's unrealizable, you want such a counterexample that optimizes some parameter, right? Maybe it's the shortest way to get to the error, or it's the one that uses the least memory, and so forth, right? So again, it is a synthesis problem. It's just that this time we're not building the implementation, but rather the counter strategy. But in a way, the same rules apply. I hope that this is sort of what you were aiming at. I mean, there's of course the bigger issue. How do we explain what went wrong in the first place? So, for example, we can look for minimal subspecifications that are already unrealizable, and all these techniques that help us understand the problem. But I think in the end, it boils down to finding the counter strategy and letting the user sort of try to do its best, his or her best against that counter strategy, because that's what proves that your problem is unrealizable. I can't see you, so you have to say whether you're happy or not.
Yeah, I'm sort of happy, yes. I mean, it explains, of course, it makes a lot of sense that if we have a strategy how to find solutions, we should also figure out the counter strategy, how to find counterexamples that we're looking for. Yeah, I was just also wondering if there is a way to automate this process such that we remember what we've found so far, or maybe such that we have some kind of automatic guidance. But it would, of course, also make sense if we have feedback from the user, and this would guide us as well.
I think, I mean, the whole question, what should be how should the cooperation work between the synthesis algorithm and the human user is one that's tremendously interesting, because the idea in Church's problem that the user writes a specification and then it's done, right? Then the algorithm takes it from there, is obviously nonsense, because you make so many errors in writing your specification. And it's not at all obvious that you're done just because the synthesis algorithm produced some solution. Because if your specification is nonsense, then why should the implementation be anything other than nonsense? So I think that's one of the reasons why you don't want to see it as a producer-consumer kind of relationship, but it is definitely one of an interaction. And I mean, there are some ideas out there. One is interactive synthesis, where you start with a small specification, and that is then, that leads to a small implementation that is hopefully small enough so that you can still understand what it does. And then you add a requirement, and then you get an explanation that tells you why the simple solution that you had so far is no longer good in light of that additional requirement. And then you get a fix that also adjusts, also accounts for this additional requirement. And now your implementation gets more and more complicated because it needs to accommodate more and more requirements. But at least you understand, and each transformation step why that step happened and what it changed in the program. So maybe this is a way to ensure that in the end you understand what the synthesis has produced. But I think, I mean, this problem has so many facets that we haven't started to understand it.
Yeah, thank you. I think this is what you mentioned. So right now, this is addressed in the ATWA paper, isn't it? From
yes.
Okay.
Very
okay.
good. Thank you.
Then I will look definitely more into this. Very interesting. Thank you.
I think we're running out of time, Ben, but your talk is really exciting. How do you have an estimate how many more minutes you have, or you have actually enough slides for 2 more hours?
No, you see, I'm through the part that covered the basic history and the fundamental algorithms. And now I have slides left that talk about some exciting directions, but I think it's perfectly fine if we don't get to those today. I purposefully did not, rush ahead because I think we'll have ample opportunity to talk about these things at other occasions. So my suggestion would be, since we are indeed out of time, why don't we just finish up at this point? I think, I mean, the bottom line for me is that synthesis has made this amazing journey from this theoretical problem to something that at least holds the promise to be really useful in practice. And it has a 60-year history, but it has tremendously taken up speed in the last, say, 15 years since the UMB Protocol and all these practical benchmarks. So I think it is a really exciting problem still after 60 years, because it has so many fundamental facets where we simply know nothing at this point. So I think it was a wonderful idea to choose synthesis as the topic of this program and this seminar. So let me close with this, and yeah, I look forward to many more discussions on this.
Okay, so I guess then I will listen to our speaker, and let's finish now. We are only 2 minutes after the time, so thank you very much, Bernd, for this fantastic tutorial. It was really great. It was exactly what we wanted to learn, to bring everyone up on the speed. And I guess you're right. We have still the whole semester ahead of us, so we will have chance to address this topic. So everyone, let's give a warm thank you to Bernd. And if you, since a person who knows him, if you have any questions or you would like to know more, just ping him. He's really, he will gladly answer. At least I assume you will.
Definitely. Thanks very much, Brigitte.
Yes, and Ben is also a participant, so you can probably just ping him at gather town coffee places and stuff. So thank you once again, Ben. Thank you. And let's go. Bye, everyone.
Thank you. Bye.
Bye, everyone.
Thank you.
Bye-bye.